So good morning, everybody. Today we are going to start with a new topic. We're going to talk about finite elements in the sense that we have learned how to apply finite elements to a simple problem, to a simple differential equation, even to Poisson's equation. And we have kind of even got to the point where we can write a small program to solve Poisson's equation using the finite element method. But what I would like to do now is I would like to kind of formalize the concepts we have started with and see what is deal a little more with the finite element stuff rather than the physics stuff. Now, for that, what I'm going to talk about is isoparametric elements. What are isoparametric elements? So when we have isoparametric elements, we are still talking about the similar kind of finite elements that we have been talking about, but they are special in the sense that they use mathematical mapping from one coordinate system to a second coordinate system. What do I mean by that? I will discuss. See, the first sentence says the concept of isoparametric elements is important when the domains acquires a complex shape. Why that is important, that context I'll come to later. Firstly, let us figure out what I mean by the isoparametric elements. Now, U starts with a physical coordinate system. So when you have the elements, you have, let's say you have a one-dimensional problem. So you're working in the X domain. So what you would be doing is your elements would be from x1 to x2, x2 to x3, and so on and so forth. So you're dealing with the physical coordinate systems involving xi. Isoparametric elements do not work in the physical coordinate system. Instead of that, what you do is you take the element in a second coordinate system. This second coordinate system may be called the local coordinate system or the natural coordinate system. So once you have defined the isoparametric element in the local coordinate system, you will have to figure out a way of mapping each element onto the physical coordinate system. So essentially what I'm saying is that you will need to take your elements and you will need to map them from the actual physical coordinate system, XYZ coordinate system, and you will have to map them into a second coordinate system. Let us call that the UVW coordinate system. Why would we like to do that, and what is the point, and what happens when we do that? Let's discuss that and then come back to why we at all need the isoparametric elements. So the problem domain is in the physical coordinate system, but we are going to work in a second coordinate system, which is the UVW coordinate system. So let us consider this element on the right. This is your element as you have been discussing. Let's say you have a linear binoded element, which is between points x1 and x2 on the XYZ plane. And therefore, you will have phi1 as the nodal variable at node 1, phi2 as the nodal variable at node 2. What I am going to do is, I am going to choose a second coordinate system, which I call the natural coordinate system. Since there is only one variable, let that variable be u. So x1 should map onto u1, x2 should be map onto u2. And additionally, u1 should be equal to -1 and u2 should be equal to +1, which means that all the points, no matter how many, between x1 and x2 should map onto the distance between the line segment between u1 and u2. So no matter what the values of the coordinate system, x1 or x2, what I am going to do is I am going to map this entire element onto this local element, which is defined between u1 equal to -1 and u2 equal to +1. At the moment, do not ask me a question why I want to do that. Just go with me. Is this clear to everybody? So in that case, what I will need to do is I will need to choose a mapping function which performs this mapping. I am at the moment going to give you an arbitrary mapping function. Again, at the moment, do not ask me from where I get this. So I will take this mapping function n1u, it's a function of u, is equal to half 1 minus u, and n2u is equal to half 1 plus u. And then what I say is, my mapping function is x equal to n1u x1 plus n2u x2. If you look at this, you can figure out that u1 maps onto x1. Can you check that quickly? With this function, does u1 map onto x1 and u2 map onto x2?
Yes, ma'am. They are mapping for value of that value of.
Yeah, u1 is minus 1, u2 is plus 1. Yes. So this is my mapping function for which I can map this particular element onto this particular element. So these are two coordinate systems. Now remember, when we use the method of weighted residual, we use a shape function for the trial function. I'm going to solve for phi. And if you remember, the weights are the shape functions. Let us imagine that this n1 and n2 that I have given you are the shape functions. In which case, phi will be equal to summation ni phi I. So over this element from u1 to u2, phi will be defined as, the trial function phi will be defined as n1 phi 1 plus n2 phi 2. Isoparametric elements are elements in which the same shape functions are used for geometric mapping and for interpolation of the nodal variable. Again, at the moment, do not ask me why. Let us go forward. So therefore, this is something that we were already doing. We were expressing phi as an interpolation function in terms of phi 1 and phi 2 with a shape function n1u and n2u. And I have given you particular expressions for n1 and n2. Why I have given you these particular functions, we will discuss later. But if I tell you that these are my shape functions, then you will be able to write phi as n1 phi 1 plus n2 phi 2. And I am saying go further and use this also, the same shape functions, use them as a mapping function to map this element between -1 to +1 to x1 to x2. Okay? So in isoparametric elements, you will use the same functions as shape functions for the geometric mapping from the physical coordinate system to the local coordinate system and for interpolation of the nodal variable. If you have done this, you can now proceed as before with the method of weighted residual. As you know, in the method of weighted residual, you will need to also find d phi dx. So let me find d phi dx for you. D phi dx is equal to dn1 dx phi 1 plus dn2 dx phi 2. Now this is n1 and n2 are functions in u. And I am differentiating with respect to x. So therefore, I will use this chain rule, dn1 du into du dx. So dn1 dx is written as dn1 du into du dx, dn2 du, du dx. If therefore I write, if I try to find dx du is on the right hand side, du dx. So let me write it as dx du. So therefore dx du is equal to dn1 du into x1 plus dn2 du into x2, which I can calculate for the given shape functions as half x2 minus x1. So automatically I get the value of d phi dx. D phi dx is half x2 minus x1 minus 1 x2 minus x1 into phi 1 plus 1 by x2 minus x1 plus phi 2. So I have found dn1 du, I have found dn2 du, I have interposed the values, and I also have found du dx also. I have found du dx, and therefore I have been able to find d phi dx in terms of the physical coordinates and the nodal variables. Remember, that is what I want to do. in the method of weighted residuals, what I want to do is I want to work with the nodal variables phi1 and phi2, and I want to use the physical coordinates. And I want to establish my stiffness matrix, obtain my stiffness matrix in terms of the physical coordinates. And I seem to be able to do that because I will be needing the values of phi and d phi dx. And as you can see, phi can be expressed in terms of phi1, phi2, and d phi dx can also be expressed in terms of phi1, phi2. So let us put it in my equation, which is the equation that we are going to use. We're going to use this equation in first one dimension, d2 phi dx square minus phi equal to 0. This is, of course, not exactly Poisson's equation, but an arbitrary equation in phi. So if I apply the method of weighted residuals to this, what I need to do is I need to obtain the integral of weighted residual, the residual r weighted by the shape function n. So as you see here, now I'm using not s or h, I'm using n for the shape function. So just keep that in mind. There is no particular reason for that, but don't get confused. So I need to integrate this between x1 and x2. So integration x1 to x2 nr dx. So let me put the value of the residual. When I compute the residual, I should always be using phi tilde because I'm not going to obtain the exact solution of phi, but an approximate solution. But as I go forth, you see the tilde vanishes. The tilde does not really vanish. I just omit to use the tilde because by this time it has been established that we are working with an approximate solution. The exact solution does not have a place here. So I'm not going to keep on trying to differentiate. So n d2 phi dx square minus phi dx, this is what I need to evaluate. Remember, I have to use the weak formulation, and therefore this becomes minus dn dx d phi dx minus n phi dx. This remains within the integral, and I need to evaluate n d phi dx between x1 and x2. This is by the separation of variables, which we always use in order to convert a strong formulation into a weak formulation, so that I only have to work with d phi dx. I do not have to work with d square phi dx square. So this is what I have. For the moment, let us ignore this term. This term can be evaluated. Let us concentrate on the integral. So the integral has to be evaluated between x1 and x2. The integral has dn dx, d phi dx. D phi dx we have already found. Let us do this. Let us write d phi dx is equal to j inverse d phi du. We have already obtained this in the previous slide. Let me try and go back to the previous slide. So we have obtained d phi dx in terms of du dx. Okay, let us do it this way. Let us do it again. So we have to evaluate dn dx. So dn dx is equal to dn du into du dx. So I can write dn, now if d phi dx is equal to j inverse d phi du, I can write dn dx is equal to j inverse dn du. So whether it is the differentiation of n or the differentiation of phi, when you are differentiating with respect to x, you need to multiply the differential with respect to u with the Jacobian matrix, inverse of the Jacobian matrix. What is the Jacobian matrix? The Jacobian matrix is j equal to dx du, which is ddu of xu. Is this clear to everybody? This is simple because we are using only one variable. So I call j as dx du, which is ddu of xu. So this is a matrix multiplication. I've expressed this as a matrix multiplication because Hitesh, you're still having problems. And admit does not seem to be working. Okay. So I am writing this as in a matrix form because we're not always going to work with one dimension. We're going to work with 2 dimensions. But in 1 dimension, it's easy. J is equal to dx du, which is ddu of xu. And this is the relation that we need between the different ddx's and the ddus. So therefore, once we have defined j, dn dx becomes equal, dn u dx becomes equal to j inverse dnu du, and d phi dx becomes equal to j inverse d phi du. So therefore, what I'm going to do is I am going to convert this entire integration into an integration in du instead of an integration in dx. Now we have mapped x1 to -1 and x2 to +1. So therefore, when I integrate over that particular element, the integration limits become -1 and +1. Where was I? So the integration becomes an integration between -1 to +1. We have dnu dx, so J inverse dnu du. Then we have d phi dx, which is J inverse d phi du. Where is that? This is J inverse dnu. Okay, so this is J inverse d phi du. Now what is phi? Phi is again n into u. So phi is, as we have expressed, where is this? Phi is again n into phi. So therefore d phi dx, once we convert this, we get d phi dx is equal to J inverse d phi du, and d phi du can be written as n into phi. So therefore the integral becomes J inverse dn du into J inverse dn du into phi. Phi can be taken out of the integral because phi involves only constant values which may be known or may not be known, but it does not need to be integrated. So this matrix comes out of the equation. And apart from that, you also have the second term n phi, which is simple and can be written as n into u into phi into u. Remember, we also have to convert the dx into the corresponding integration, and dx is not du but j into du because of n into x. So therefore, this integral now, which I had in terms of x between x1 and x2, is converted into an integration in terms of u between -1 to 1, and it involves the J inverse matrix, the dnu du term, the phi matrix, and n into phi. So this is therefore what you need to integrate, and this will give you the K matrix or the stiffness matrix. N phi will of course give you only the, will it add to the force vector or the stiffness matrix? You have a phi here. What will you do with n phi? I haven't done it here.
It will add to the stiffness matrix.
It will add to the stiffness matrix. I have left it undone. So phi u also has to be expressed in terms of n phi, and you will again have phi, the matrix coming out, and n into, again, you'll have another n matrix, which will go into here. So this will also add to the stiffness matrix. So entire thing that you have here will add to the stiffness matrix. So is this point clear to everybody? What I have done is I have applied the method of weighted residual. I have applied the weak formulation, and therefore I know which integration I have to perform over dx, over the elements, and applying the shape, using the shape functions as my mapping function here, using the shape functions as my mapping function as x equal to n, n1, n2, x1, x2. So using the shape functions as my mapping functions, I obtain this integration in terms of an integration in U, where the integration limits are -1 to +1. So I think you probably begin to see why I am going through all this rigmarole. Any guesses? Firstly, any difficulties, any questions so far? Do you understand the manipulations? Do you want me to go over them again?
Yes, ma'am.
Right, I thought so. So what I'm doing is I'm taking the physical coordinate system. I have an element x1 to x2. The values at x1 and x2 are phi1 and phi2, just as we had before. I am going to apply the method of weighted residual. But before that, I decide to use isoparametric functions. Isoparametric functions are not defined in the physical coordinate system. Isoparametric functions are defined in a second coordinate system, which we call the local coordinate system or the natural coordinate system. So in this local coordinate system, I'm telling you what the isoparametric element should look like. I don't give you a choice. I give you an element which goes from node 1 to node 2, local node 1 to local node 2. Local node 1 is u1 equal to -1, and local node 2 is ut equal to +1. Now, therefore, if I need to map this entire element spanning from x1 to x2 to this particular element, I will need to map x1 to u1, x2 to u2, and any point lying between x1 and x2 will be mapped onto the points lying between u1 and u2. You can find the points. Now, how do you decide? At the moment you don't decide, I tell you a priori, use this mapping function. N1 is a function of u equal to half 1 minus u. N2 is a function of u equal to half 1 plus u. Which means for the mapping function, I have x is equal to n1 x1 plus n2 x2. Now this should ring a bell immediately, because we have been, if these were not arbitrary mapping functions, but shape functions, we would use this mapping function or interpolation, we would use this interpolation function phi equal to n1 phi 1 plus n2 phi 2 to define the function phi over this element in the local system. So what phi is that I write in the next slide, phi is the function phi, the trial function phi obtained in this element between u1 and u2. I'm also telling you that in isoparametric elements, what we are going to do is we are going to use the mapping functions as the shape functions. So if I have used n1, n2 as my mapping function, I'm also going to use n1, n2 as my shape function. So not only is x equal to n1 x1 plus n2 x2, phi also is equal to n1 phi 1 plus n2 phi 2. Now, what do I need to do? I'm using this equation. I'm going to apply the method of weighted residual to this equation, d2 phi dx square minus phi equal to 0. So first I need to multiply by the residual, obtain the residual. The residual is d2 phi tilde dx square minus phi tilde. This is to be integrated in the x domain between x1 and x2, and I'm going to use n as my weighting function. So if I do this, the first thing that I need to do after applying the method of weighted residual is I need to use the weak formulation. So I use separation of variables to break this d2 phi dx square into this term, this first term, and the third term. So I have minus dn dx d phi dx, and then I have within the integral, and then I have n d phi dx between x1 and x2. For the moment, let us ignore this, these values, these constants that we will get. Let us for the moment ignore these values. Why we will ignore these values, you already know, but I'll discuss later. So let us concentrate on this integration. This integration is an integration in terms of phi and n dx in the domain x between x1 and x2. But then n is a function of u. Initially, you remember the shape function was a function of PQR, and PQR were functions of the physical coordinate system. But here you have a function n, which is a function of u. So therefore, you cannot straight away evaluate this integral. You will have to go from u to x. And what I will do is I will convert this entire integration into an integration in u, and I'll perform the integration in the u domain. That is my objective. So I have to convert this into an integration in the u domain. So I need to evaluate dn dx. dn dx is equal to dn du into du dx. I need to evaluate. So let me do this. What I do is I write Hitesh. So I write this in a matrix form as dn dx, j inverse dn du. Here the matrix form doesn't make any sense because you only have one element, but you know that if you don't have a one-dimensional problem, you will have more than one element. So I am defining a Jacobian matrix J, which is J equal to dx du. And dx du is ddu of xu, because I have expressed x in terms of u1 and 2. So J is the Jacobian, which is ddu of xu. I'm expressing everything in the matrix form. So I have evaluated d and dx. The next thing I need to evaluate is d phi dx. D phi dx will also be similarly equal to J inverse d phi du. I need to evaluate n into phi. N is a function of u, and phi is now a function of u because phi is n1, phi 1, n2, phi 2. So therefore, phi u will be equal to, phi u will have to be written again as phi equal to n into phi 1, phi 2. So nodal vector. So keep differentiating between the function phi and the nodal vector, which involves phi 1, phi 2, etc. So the function phi can be expressed as matrix n into the vector phi. So that's exactly what we will do, but I haven't done it here. I have not, I've left the first term, the second term as it is. I have not taken out the nodal vector here. Sorry. So now, also when you perform these integrations, convert these integrations, you have to remember that dx is also not equal to du, but dx is equal to j du. So this is the integration that you need to perform. And if you take out phi u and express that as n into phi matrix, phi nodal vector, you can take the entire nodal vector out of the integration, and whatever remains within the integration will be like your ku equal to f. So you will have, or k phi equal to f, so k will be the stiffness matrix. And to evaluate the stiffness matrix, what you need to do is, you need to perform this entire integration in the domain u between points -1 and +1. Is this clear now?
Yes, ma'am.
Right. So the next question is, if you have understood what I have done, you have just realized that all I have done is a lot of algebraic manipulation to convert an integration that was to be performed in the x domain, and you want to perform it in the u domain. Why? Any guesses? Why would I like to perform the integration in the u domain, which involves so many more extra manipulations? Why would I, Are Baba, why would I want to do that?
Here the integration is between -1 and 1.
Yes.
So
how do you think that will help you?
maybe in computation it will help.
Yeah.
Ma'am, we are ignoring that n d phi by dx
For the moment,
x2.
yes. For the moment, yes. I'll come back to it later. That's not an integration. Those are some constants, right?
Yes, ma'am.
Any guesses why I'm ignoring them? You have to think in terms of it had in the previous class, yesterday's class.
Maybe we'll add that to the force. What's
your x1 and x2? So this term n d phi dx needs to be evaluated at points x1 and x2. x1 and x2 are what?
Coordinates.
Of course. What coordinates?
Ma'am, they are the nodes. X1 and x2 are the nodes.
Yes, and we have taken elements which have nodes only at the boundaries. So when you add up this particular integration, you will perform for every element, and you will have contribution from every element. What happens to the values that you evaluate at the internal nodes?
They will cancel out.
They will cancel out, and you will be left with the outer nodes. So maybe x1 and x6. I mean, if you imagine that, if you go back to the grid that we were working with in the previous class, so we had a straight line which was, the first node was x1 and the last node was x6. So the middle nodes x2, x3, x4, the contributions will cancel out, and you will only need to evaluate this variable at node number 1 and node number 6, which are your boundaries to the entire geometry. And when you do that, you will know the value of phi at x1, you will know the value of phi at x6. So you will not need to do any kind of computation. You can actually evaluate, and either it will come out to be 0 for Dirichlet boundary condition. You don't need to evaluate because phi1 will not have to be solved for. For Neumann boundary condition, it will vanish. If it is a non-zero Neumann boundary condition, you will get some component which will add up to the force vector. So all that we need to recognize at this point is this term does not contribute to the stiffness matrix, but contributes to the force vector depending upon the boundary conditions. So at the moment, we don't need to bother about them. I mean, you will need to bother about them when you actually do the computation, but right now we don't need to bother. Right now, we will just go ahead with the computation. We know how to deal with this, right?
Yes, ma'am.
Now, as you can see, when you do all this, you actually require much more computation. You have to find a mapping function, you have to do chain rule, etc., etc. So why do all this? What is the advantage? The advantage is, of course, as Ashok guessed, it is in the evaluation of the integration. You can use numerical techniques for integration. And if you want to use numerical techniques for integration, performing an integration between -1 to +1 will become easier. And the advantages will really, even though you have to do more computation, it will be advantageous when you are dealing with irregular domains, even if you are not working with straight lines, straight elements, or you're rather working with curved domains, you're working with geometries which are very difficult, very convoluted, you're working with differential equations which are complex. Basically, the idea is that it is easier to perform this integration in the U domain using numerical techniques rather than performing it in the X domain. And what are the advantages? We will discuss later. So essentially right now, just accept that this is the only reason that we are doing all this is because we want to use numerical integration for numerical techniques for integration. Now, do you know any techniques for numerical integration? Do you know
Yes,
any?
ma'am, the Simpson's 1/3 rule and the trapezoidal.
Simpson's 1/3 rule, trapezoidal rule. In all of this, what exactly are you doing? See, in integration, what you need to do is you need to you have a curve. When you need to integrate, what you need to do is essentially you need to find the area under this curve, the entire area. Now, when we perform a integration in the continuum region, when you perform the integration in the continuum region, what you do is you find the total area under this curve. In numerical techniques that you're talking about, Pratasha, this Simpson's rule, etc., what you essentially do is, for example, let's take the trapezoidal rule. In the trapezoidal rule, what you do? What you do is you draw a trapezoid. And when you draw the trapezoid, remember what will happen. You will be approximating the actual curve with a straight line. And what you do is you find the area of this trapezoid. And there is an error because this straight edge of the trapezoid does not necessarily match with a curved spline. So you get errors because of that. So essentially, you're breaking up the area under the curve into small domains, regular domains, and you are evaluating the area of each of these domains and adding up the total number of rectangles or trapezoids that you make. You add up the sum total of the area of the n number of trapezoids, and that's what gives you the trapezoidal rule. The other rule, that our 1/3 Simpson, is also a variation on that. We are going to do something similar. But we are going to use the Gauss quadrature method. Now, let us stop talking about the elements and let us talk about the Gauss quadrature method as a numerical technique for the moment. Now, as all integration methods in when you use numerical techniques to evaluate an integration, you actually need to convert that into a summation, as I just discussed. So therefore, if you have a function fx, so this pink line is your function fx, which is an arbitrary function. I don't know what kind of function it is. And I need to evaluate it. I need to integrate it over the domain a to b. A to b is not marked here. Let's say this is a and this is b. To perform this integration from a to b fx dx, I say that integration a to b fx dx is equal to the limit of the summation fxi dxi over I equal to 1 to capital N in the limit that small n tends to infinity. What do I mean by that? Basically, what I'm saying is I am going to evaluate, let's say this is my point xi, and I can sample fxi. In the trapezoidal rule, or if you're just using rectangles, what you would do is you would evaluate this function, this area. So what I'm saying is, let us take this point xi and let us consider, I would like to, okay, I can't change this now. Let's say what I do is I want to make a small modification to this. Let's say xi is the midpoint of this. And at xi, I choose the value of fxi, okay? I can take the value of fxi from the pink point. And around this xi, I choose choose a rectangle or a trapezoid. Let's say for the moment we'll choose a rectangle of infinitesimal length or infinitesimal width. And then I will, so that is my dxi. This is my dxi. So when I multiply fxi sampled at point xi and multiply that by a very small interval dxi, I get this area, this blue area. And then I sum over all such areas from I equal to 1 to capital N for infinite number of such points. That should give me numerically the integration. In that case, I can also write it like this, that the integration is, in a way, a summation of fxi multiplied by some quantity delta xi, some differential or some difference about xi. So instead of taking a very small infinitesimal width, I take a finite, because numerical techniques, I cannot work with infinite quantities. I cannot really work with n going to infinity. So I will need to take a finite number of widths, and this finite number of widths, finite number of rectangles, and therefore there will be some non-infinitesimal thickness to my xi. So instead of taking dxi, I now say this is delta xi. How I choose delta xi, I'm not saying at the moment. So I am converting this integration to this is equal to, this is the exact value. I am converting this integration to an inexact value, an approximate value. And what I need to do is I need to do summation fxi into delta xi, where fxi is the value at a point xi of the function, and about this function I will choose a certain interval of x delta xi. And here in this case, n is no longer infinite, n is a finite number, which means I will get an inexact value. Is this clear to everybody? This would be true for any numerical integration. That is the only way I can deal with numerical integration, numerical technique for integration. Now, if you look at delta xi, it is a kind of weighting function. which varies from xi to xj. So at every point xi, what I do is I can consider this delta xi to be a weighting function wi. Where this weighting function will come from, I'm not telling you at the moment. So I can therefore replace this integration as integration a to b fx dx is approximately equal to summation I equal to 1 to capital M. Now I'm going to talk about M. In summation I equal to 1 to M f xi wi. So xi is the points, are the points. There are M number of points. And at each of this M number of points, I'm sampling the value of f. I'm sampling the value of the function at these xi points. So I will call xi the integration or the sampling points. And at every value, at every xi, I will sample the value of the function, and then I will multiply it by a weight function, which is also variable, varying from point to point. So for example, this is delta xi. I no longer say that this is delta xi. I just say that every point xi, there is a weighting function wi, and I will call that the weighting coefficient. So you can interpret it as the width of the rectangular strip whose height is fxi. Just as I said, delta xi could be the width of the strip, and multiplying fxi by this width of the strip should give you the area of this blue region. So you can interpret it like this. It is somewhat analogous, but I am going to give you the values of xi and wi. How I will give you, I'll tell you later, but what I'm saying is in Gauss quadrature, the integration is converted into a summation over m number of integration points. And at each of these integration points, I will sample the function fxi, and I will weight this value with a weighting function wi and take a summation over all the points. Is this point clear? Is the idea?
Yes, ma'am.
Yes, ma'am.
Now, where will you get the values of xi and wi? I will give them to you. I will give them to you, or rather Gauss quadrature. There are Gauss quadrature integration tables which give us standard values of integration and weighting coefficients, but those are only defined over the domain -1 to +1. So if you, I'm going to do this later, I'm going to show you one of the Gauss quadrature tables, and you will see that in Gauss quadrature tables, you are given that if you are integrating over a domain -1 to +1, what are your sampling points, x's? How many sampling points do you need? So the value of m is given to you. What are the sampling points? So x's are given to you. So you can evaluate f at these x's, and the weighting coefficients are also given to you. So now you know that the reason that we mapped the x domain onto the u domain is so that we can directly use Gauss quadrature, because Gauss quadrature values are all given in the naturalized domain. It is not given for any arbitrary physical system. It is given in the domain -1 to +1. And that is what we are going to do. So right now, what we have done is we have written out the integration in terms of u, and we are going to evaluate the natural domain, and we are going to evaluate this term using Gauss-Legendre quadrature. Why are we going to use this particular technique? Gauss-Legendre quadrature tells us that a polynomial function of order 2n-1 can be exactly integrated using an endpoint quadrature. So if you go back to the previous slides.
Ma'am, one small doubt, ma'am.
Yes.
So by exactly integrated, I mean with zero error.
Yes.
Oh, okay.
So exactly what you would have got if you had integrated over the continuum when an analytical solution exists. That is what it is. So you see, what I'm going to do is I have written integration a to b fx dx is approximately equal to summation I equal to 1 fxi wi. So this is an approximate estimate. But what I am saying is that if you fix the number of integration points in a particular way, following Gauss-Legendre, you will not get an approximate estimate, you will get an exact estimate. When will you get that? Your fx, if your fx is a polynomial of the order 2n minus 1. In that case, if you use an n-point quadrature means m equal to n, you will be getting an exact value. So, for example, you have a linear polynomial. What point quadrature should you use? Before I go ahead, I'll show you what a Gauss table looks like. This is what the Gauss quadrature table looks like. So these are the abscissa and weight coefficients of the Gaussian quadrature formula applied over -1 to 1 fx dx. So if you're integrating the function fx dx, any function fx dx in the region -1 to +1, what you have to do is you have to sum over hi fai. What are the ai? So you have n equal to 1, that is your 1-point quadrature, m equal to 1. So that this point is 0, and at 0 you need to evaluate f0, and you have to weight by the weighting coefficient 2. Similarly, you have 2-point quadrature, 3-point quadrature, and so on and so forth. So this is what it looks like. Now let us go back to the question we were discussing. Suppose you have a linear polynomial. X plus b is equal to 57. And okay, so you need to integrate this polynomial between -1 to +1. What point quadrature would you need to use? Read the statement: a polynomial function of order 2n minus 1 can be exactly integrated using an n-point quadrature. Nishant?
1-point quadrature.
1-point quadrature, why is that?
The polynomial which you mentioned, it is a first order polynomial.
First order polynomial, yes. So 2n minus 1 is equal to 1. So n is equal to 1. Yes. For what is the highest order of the polynomial for which you can use a 1-point quadrature? Did you get the question?
Yes. Can you please repeat the question?
So if you have a linear polynomial, you should be able to get the exact integration using a 1-point quadrature. Now, if you go on to higher polynomials, what is the highest order polynomial which can be exactly integrated using a 1-point quadrature?
Ma'am, it will be 1.
It will be
Exactly,
linear.
if you want to calculate, it will be 1.
It will be 1. If I go for a second order polynomial, what happens then?
It will be 2-point quadrature.
Why?
Oh, sorry, second order polynomial.
Second order polynomial, huh? So why would I need to use, you're saying that for a second order polynomial, I need to use 2-point quadrature. Why is that? How did you work it out? That is my question.
No, for second order polynomial also we'll need 1-point quadrature.
Why?
Because 2n minus 1 should be 2. So we'll get n as 1.5, but we cannot have n as 1.5. So we'll take minimum 1 because
Why
we
would you
cannot
take
take 2 also. If we take 2 quadrature, then what will happen is that the area of integration that we are estimating for numerical technique will be more. So we'll take lesser areas.
No. You don't make up your own rules. The rule is given to you.
But we cannot have 1.5
You cannot
point.
have 1.5. So if
Yeah.
you use a 1-point quadrature, you will not get the exact value.
No, we will not get. The error
If you
will
use
be
the
more.
2-point quadrature, you will get an exact value.
For 2.
You need to use at least an n-point quadrature to exactly integrate an n-point 2n minus 1 polynomial.
Okay.
So let's take the case of 3. What happens with 3? A third order polynomial.
So third order, it will be 2-point quadrature.
2-point quadrature. So the third order polynomial will work, you will be able to integrate with a 2-point quadrature. Now, actually, you don't really need a 2-point quadrature for a second order, but 1-point quadrature doesn't give you the value. So you will have to go for 2-point quadrature.
Okay.
Wait a minute. So now you know why we are trying to use the Gauss-Legendre quadrature, because even by using a numerical technique, we would be able to obtain exact integration. But do you see a catch here? I am saying that if you have a function fx, and if it is of 2n minus 1 order, and you use an n-point quadrature, you will get the exact value, which means that even though you're using a numerical technique, you're going to get an exact solution, which is an advantage, and therefore I'm going to use Gauss quadrature. Which sounds very nice, but in the finite element method, you will be looking for fx. You don't know fx. So how will you choose which point quadrature to use? You understand what I'm saying?
Do you mean that we will not know the order of the polynomial because we will?
That's exactly what I mean. So this works very well only if you know the order of the polynomial fx that you're trying to integrate. You may not know that. Okay, is this clear?
Yes, ma'am.
And we also talked about a degree of precision. The degree of precision of a quadrature, so whatever quadrature you're using, the degree of precision is the degree of the highest order polynomial that can be exactly integrated. So for example, a second order Gauss rule has a degree of precision of 3, because if you go to 4, you don't get an exact solution. Now this is for a one-dimensional case. Now we have also dealt with two-dimensional problems, and therefore we will have to perform integrations in two-dimensional regions. So you may have a region like this. You may have an integration like this. F uv, f is a function of u and v. F uv minus 1 to plus 1 du dv. This needs to be integrated. This can be written as summation, two summations, double summation. One is the summation over I, and the other is the summation over j, wi wj, f ui vj. So what this essentially means is that if you take this case, Darshan, you wanted to leave. Should I stop now or should I continue for a couple of more minutes?
I can continue.
Okay, just let me finish this off. That will kind of finish off the. So let us imagine that I want to perform an integration of a second two-point quadrature over two domains. Let us have fxi. Can you write out, one of you? Can you write out the integration in terms of the summation? I want to integrate using two-point quadrature an arbitrary function fx y in 2 dimensions. So I want to evaluate integration fxy dx dy. How will I perform this integration? I want the terms that you will have in your summation. Can you see this? Well, let me stop sharing. Are you seeing this, Ulta?
No,
So
ma'am,
we
it's
are seeing
it's
it
perfect.
right.
Okay, I'm seeing it, Ulta, no problem then. Yeah. So this is what I want you to evaluate in terms of the summation. I will give you, again, I will give you the Gauss quadrature table. So yeah, you can tell me. So look at the Gauss quadrature table and tell me. How many terms will I have in this summation? I'm going to use a 2-point quadrature. So it's a 2-degree polynomial. I'm going to use a 2-point quadrature. So n equal to 2. What are my sampling points? Sampling points are plus minus a. So the sampling points are plus minus 1 by root 3, right? Plus 1 root 3 and minus 1 by root 3. So give me the sampling points in the xy domain. So I will evaluate f where? What is x1, y1, x2, what is x1, x2, y2, what are the points? How many points will be there in total? Why has that flummoxed you? Okay, let us do it in one dimension. Integration minus 1 to 1 fx dx. Tell me a second order polynomial. Tell me the terms for the summation. Integration fx dx minus 1 to plus 1. Darshan?
When n is equal to 2, it will have 4 terms.
I am only considering one dimension now. Minus 1 to plus 1 fx dx.
And
So there
then
can only be 2 points, 2 terms, because you have 2 points. So this will be f evaluated 1 by root 3. At 1 by root 3, its weight is 1 plus f evaluated at 1 minus root 3. Again, the weight function is the same. So this is what it is. Do you accept?
Ma'am, the polynomial was second order.
Yes, I told you. Let us assume that f is a second order polynomial. So I'm going to use this 2-point quadrature. So this is
ma'am,
how I evaluate it.
Yes, ma'am.
ma'am, 1 by root 3.
F at 1 by root 3. 1 by root 3 is my sampling point given by the Gauss quadrature table.
Okay. But ma'am, the second order polynomial will be like x square plus 2ax plus a square, right? Like we'll have 3 terms.
Yeah, you are evaluating. So when you evaluate at a particular point, when you evaluate f at a given point x, it's a constant that you get. No matter what terms, you can add them up.
Yeah, that is okay.
Yeah, you're getting confused. Let's say f is equal to, fx is equal to x squared.
Plus 2ax plus a square.
अरे a मतलब x squared plus 2x plus 3.
Ma'am, this method is only for the integration. So we should know, means we know the functions. Means I think
Yes.
Pratyasha is asking if we don't know the function, but
Exactly. We know the function at this
we
point.
know the
At
function
this
and we
point,
just
know
want
the
to
function.
integrate that.
Yeah.
Okay, okay. And we know the sampling points also.
You know the sampling points, you know the weight functions corresponding to every sampling point. So what I do is I evaluate f at 1 by root 3.
Mm-hmm.
I evaluate and weight it by 1, the weight function 1, plus I evaluate f at minus 1 by root 3 and multiply again with the weight function, which is 1. Okay. So this is your
how did we how did we calculate the sampling points? Like, is it
given.
given?
It is
After I finish showing this, I will go back and show you the Gauss quadrature table once more. So this is for one dimension. Now, suppose I want to evaluate this. Suppose it is no longer a function of just x, but a function of fxy. And I need to evaluate a double integral. Darshan, if you need to leave, you can leave. I now want to evaluate this. And I don't have any extra information. I just know that my sampling points are, I'll write down what the Gauss quadrature table tells me. Gauss quadrature tells me that for 2-point quadrature, the sampling points are plus minus 1 by root 3. And at each of the sampling points, the weight function is 1. This information I have, and I have used it for one dimension. Now, question is, if I have a quadratic polynomial in x and y, and therefore I know that I need to use a 2-point quadrature, what will be my summation? What will my summation look like?
It will have 4 terms.
4 terms, yes. And what are these 4 terms? So this
For
will
1 by 3, 1 by root 3, 1 by root 3, then 1 by
yes,
root 3 minus 1 by root 3.
yes,
Then for minus 1 by root 3, again 2 terms, 1 by root 3,
yes.
and then minus
So
1 by
x
root 3.
goes from x will vary. You will have to take 2 x's plus 1 by root 3 minus 1 by root 3, y also plus 1 by root 3 minus 1 by root 3, and so you will add up 4 terms. So this is exactly what I was saying, that okay, you can have a look at the Gauss quadrature table. This is what it looks like. So as you can see, the sampling points are plus minus a, so plus minus 1 by root 3, and the weight functions are 1. When you go to 3 points, then this is plus minus root over 0.6 and 0. And the weight function for the plus minus root over 0.6 is 5 by 9, and the weight function for 0 point is 8 by 9. So you can read out the values of the sampling points and the weight functions for every whichever point. Once you have decided what point quadrature you need to use, you can read out the values from the Gauss quadrature table, and then you can apply them. When you are going to a multidimensional integration, you can simply have multiple summations. So I'll stop here today, and you can perform a few Gaussian integrations to practice, and you can see how, whether you get the exact solution or not, you can check that. I'm not going to set this as an assignment, but please do it so that you get a better sense of how to use the Gauss quadrature table. You will need to use the Gauss quadrature table. Okay. If there are no more questions, we'll meet tomorrow.